So we learned about the logic gate, basic logic gate in the previous class, okay? And then, so actually, I don't believe it is tricky. So, so actually, so it's very, as I mentioned, so it's similar to the 1 plus 1 equal 2. So it's very basic, so arithmetic, okay? So, but, so, it's just the definition. So which means that you need to memorize the definition of basic logic gate. So it means the input is given, then output is generated. So you need to know which output is generated by the input signals. Okay, but actually the name of the logic gate is it's a logical. So it means that we can actually we can estimate the operation of the basic logic gate based on its names. Okay. Okay. And then actually, as I mentioned, so our complex digital systems are built using these basic logic gates, right? So actually, this is the start point. Okay, but it's just very similar. So our complex mathematics equations are built from very basic arithmetic definitions, right? So it's the same to the digital system design. Our complex systems are, it can be implemented using very simple logic gates. Okay, I think it's, I don't think it is difficult, right? So you can just memorize. Then in the previous class, we just mentioned the noise. So it's actually the real world issue. Okay. So as I mentioned, the electric devices, digital electric devices are built using electric circuits. Okay, and then electric circuits handle voltage level. Okay. And then these voltage signals are actually analog signals, right? It's not digital. So based on the discipline, it's the digital design concept, we just think that the high voltage is 1 and then low voltage is similar to ground. Low voltage or ground is 0. But actually, we need to decide the which range of the voltage is 1 and which range of voltage is 0 in the real world, in the real circuit. Okay. And then, so it is because actually in the real circuit, the noise can be included, the noise can be added, and then noise actually change the value of analog signals. So which means that if the values are changed, then the value, also the digital value can be changed. But the advantage of a digital signal is that the digital signal is tolerant to the noisy signals. Okay, so it means that even though noise are included in the original signals, the output of the digital circuit is usually does not change it. Okay. Sorry. This is the benefit of digital design. Okay, so and then so actually in this class, so in this time, so I will discuss about some physical issues. So which means that so real circuit issues of the digital system. So I frequently use the word physical. So and then actually, so you can think that our physical is related to some physical ability or some physics like bully in Korean. But actually, in our computer systems, the physical represent real. Okay. So physical means that it's a real world, issues or real world devices. Then what is the opposite concept of physical in computer systems? The physical means actually real. So the opposite word of the real is not real, unreal. It's virtual. It's not real. So actually, we can say that a physical is related to the hardware, right? Because it works in the real world, and then virtual is the software actually. So, so sorry. So you can easily heard that you can easily hear that some terminologies such as physical or virtual. So then you can think that, oh, physical, that is the real issues or real aspect of the system, and virtual means the some kind of software related aspect or some issues. Okay, so you can just understand like this. Okay, so so in this class, so we will discuss about the physical issues of digital systems. So that means it's the real implementation issues or real some device issues or real device characteristics of digital systems. Okay, so actually we need to decide. So as I mentioned, the digital devices or some electric circuits. So electric circuits and the voltage levels. Okay, voltage level, and then these voltages, these voltage signals change from ground. So we can say that ground is the 0 volt, and then to the VDD. So VDD is the supply voltage. It's the supply voltage. So what is the supply voltage? So if we generate, if we build a circuit, okay, then the circuit is can be built like this, okay. So we can easily say that, oh, this is a battery, right? It's a battery. And then this is a resistance, some devices, okay. And then sorry. So, so, so we already know that the battery has cathode and anode, right? So like the plus node and then minus node, okay? So we can say that this minus node is the ground, okay? And then the plus node is the VDD, the supply voltage. So actually, in order to run CPU chips or some processor chips, then we need to connect the some electric source, which means that we need provide them some high voltage, it's a supply voltage to the processor chip. So we need to also connect the ground, because so voltage just represent the some differences between the high voltage level, the high voltage level or low voltage level. It's similar to the potential energy of gravity. Okay, so actually, so when we implement a circuit, then the circuit signals, analog voltage signals changes from ground to VDD, it's a supply voltage. And then usually for the modern CPUs, we use the 1 volt, 1 volt for the some VDD level. So it was higher in the previous generation of the CPU, but recently the most CPU use the 1 volt for their supply voltage level. So which means that so voltage level changes from the 0 volt, it's ground, and then 1 volt, it's VDD, and then the signal changes from 0 to 1 volt, and then we need to translate this analog signal to the digital values, right? And then actually in the previous class I just show that. So we can just set up one threshold level, and then if the voltage level is higher than this one threshold level, then we can say the voltage is 1 and this is 0, right? That is how the digital signals are translated from the analog signals, right? Okay, sorry. So, but it's not actually because because of noise, actually the noise can be added to the original signal, and this approach is not good for the device. So it is because near the threshold, the digital values can be different from the original signal value, right? So it's not allowed actually in the real circuit. So then what is noise? So noise. So actually there are many noise sources in the real circuit. Okay, so we can say that the resistance, the circuit has the parasitic resistance component, 기생 기생정, the parasitic resistance component. Also, our power supply logic, the power supply component is not perfect. So which means that even though like the battery provides some high voltage like the VDD to the circuit, but this power supply component is not perfect. It's not always VDD. Also, the supply level also fluctuate. Okay, it changes because of noise. And so actually, there are many noise sources in the real world. Actually, so it's true in the real our society and the real world. Actually, right? There are many noise sources. Okay. So, and then this is some example. So this this is the buffer or its driver. Okay, it's a buffer. And then let us assume that the VDD, the supply voltage is the 5 volt. Okay. Okay. Then this driver or buffer can provide the 1. What is the 1? 1 is the digital value 1. And then it means it's 5 volt. So 5 volt is driven by 5 volt is driven by this buffer. So I said the word driven, so which means that the 5 volt signal is generated. So 5 volt output signal is generated, and then it is said that it's driven. Okay, so that's why this one is called the driver. Okay, so 운전하는 사람이 아니라 the driver means that driver means it's a component that generate output signals. Okay, it's driver. So a driver, so buffer is also a driver. So buffer can generate the 5-volt signal is a 1 in this the system, but because of noise, it's like so because of parasitic resistance component, this voltage level can be reduced, okay, because of resistance component of wire, okay. So we can say we can simply say that a metal wire is a conductor, but it's not a perfect conductor. So it has a parasitic resistance component. So voltage level can be reduced when the signal arrives at the input port of the receiver. Okay, so this is the input, and then this is the output of the component. So we can just connect the output port of the driver to the input port of the receiver. Then the signals can be delivered to the receiver, right? But actually, even though this driver generates the 5-volt of signal, but when the signal arrives at the input port of the receiver, then it can be reduced. Actually, it reduced. So it can be 4.5 volt. Then how can we handle this signal, this input? How can we translate this input signal? Okay. So actually in a real world circuit, then we need to handle this situation. So no, it's a little bit small. So this is the some oscilloscope screen of the some real clock signal. Okay, so and then we did not learn about the some clock signals, but clock signal actually digitally looks like this. So rectangular signal. Okay, and then this rectangular waveform is repeated. Okay, this is the clock signal. But if you see the real waveform of this clock signal, then you can find that it's not clean, right? So ideally, the signal needs to look like this, okay? But in the real world, because of noise, the signal levels are distorted. It's changed from the original value. Okay, and then actually the electric devices like the some digital electric devices need to handle these issues. And then I also mentioned that our basic logic gate, we can build basic logic gate using electric devices, right? So which means that our basic logic gates needs to handle these issues. Okay. So because of this issue, then we need to define some output range, allowable output range of a device, and then the allowed the input range of a device. So and then actually when we design an electric circuit, then we need to consider which output can be generated, which range of output can be generated from a circuit, and then which input can be received from other circuit. So actually the circuit can work normally within this range. So which means that we can guarantee the normal operation of a circuit or device if the signals are received or generated from other circuits or this circuit. Okay? Let's explain. I will explain. So this is the same example, right? So driver is a buffer, right? It's a buffer. It's a basic logic gate, right? It's a buffer. And then buffer is connected to other buffer, okay? So receiver is here. This is the other buffer. Let us say that this is buffer A. This is the buffer B. And then we can connect the output of buffer A to the input of buffer B using the metal wire. Okay, it's a wire. So, which means that this driver. So actually, when we learned about some logic, the buffer logic gate, then we can just learn that this is the input A, and then this is the output, and then input is 0, then output is 0, and then input is 1, and output is 1. So we can understand the behavior of buffer digitally like this. But actually, in the real world, then this driver, the buffer, can generate a voltage levels from ground to VDD. Okay, so like the 0 volt to VDD. Okay, right. But because of noise, then the original signals can be also distorted. So we need to decide which range of signals can be generated from this buffer A. Do you understand? So actually, this buffer can generate output signals from a range from 0 volt to VDD, but it's not allowed, right? So because of noise, then actually digitally we can say that this buffer can generate 0 and 1. That's it. But in an analog manner, then this buffer can generate a range from 0 volt to 5 volt. But we need to decide which range of voltage are allowed for this buffer. Do you understand? Okay. So, okay. So let us assume that this buffer A generates value 1. Okay, this is high voltage. Okay, then how can we define the allowable range of this high voltage generated from buffer A? We need to decide actually. Okay, because this buffer is not a perfect device, then the output signals can have some various values, right? Some different values. So we need to decide some logic high output range of this buffer, okay? And then which means that when this buffer A generates signal 1 is a high voltage, then this range of output is allowed. Okay, so we can say that this buffer generates signal 1, then it can be, so this signal can be ranged from VOH, this is some low threshold, to the VDD. Okay, so this is the allowed high voltage level generated by buffer A driver. Okay, it's the same to the low level signal, low level voltage, like value 0. So this range of signal can be generated from buffer A. Then the buffer B receives the output voltage level from the buffer A, right? So which means that buffer B can receive some output from the buffer A. But because of noise, then this signal can be also distorted. It's a change. Okay, so which means that this receiver, the buffer B, needs to allow the wide range because of noise. Okay, so it should be tolerant to the noise. Okay, tolerant to the noise. So actually, for the receiver, it allows the wider range for the input signal. So which means that it means it's the logic high input range. It means that if the voltage level is within this range for the input signal at this point, then this receiver, the for B, think that this is the value 1. Okay, so as you can see, you can observe that this range, the logic high input range is wider than the logic high output range. So this is because of this system need to be tolerant to the noise. Also, the low level is also the same. This range is wider. Okay. So which means that if the input signal, this signal voltage level is within this range, then receiver for we think that this value is 0. So we can decide the allowable output range or allowable input range of devices like this. And then as I mentioned, the input range is wider than the output range. So it is because of the system. The system needs to be tolerant to the noise. Okay. So this gap, the difference between logic high input range and the logic high output range. So this gap is called the noise margin. So what is margin? What is the definition? What is the meaning of margin? It's allowable value or allowable amount of some values. So noise margin exhibit that this amount of noise is allowed. So which means the noise. So there, as I mentioned, there are many noise sources. So the signals can be also distorted because of noise. But this amount of noise is added, then the circuit will work correctly. Okay. But if the noise, the amount of noise is larger than the noise margin, then the circuit may work incorrectly. So noise margin is the allowable amount of noise in the system. Okay. And then we can define the high noise margin is the gap between the logic high output range and the logic high input range. And then low noise margin is the same. That is the difference between the logic high output range and logic low output range, and then logic low input range. Okay. So I mentioned that. So the system, actually the system needs to work correctly. So which means actually we need to design a system considering some noise signals. Okay. So this is some example. So we can define some range of output signals of driver, and then also we can define some range of allowed input signals. Okay, then we can just define the noise margin of this system, which means noise margin represent the amount of noise amount of allowed noise in the system. Okay, so it means this system is tolerant to this amount of noise. Okay. Then let us assume that the input value is in this range. Then the circuit will work incorrectly. So this is the forbidden zone. Okay. So actually, in the real system, real this the system, so we need to define the this characteristics, the voltage level characteristics of the circuit. Okay. And then, so the output, the driver, then we can think that, oh, this is the 1 and this is 0. And then for the input side, the input of this receiver, the input consider that this range of signal is 1 and this range of signal is 0. But we can say, we can observe that the range is different for the output and input. Okay. So, okay, so it's 0, 0, so ground is a ground, and then it's a VDD. I said that the voltage level changing like this. So in the previous class, I just explained like this, but there is one threshold, and then we can compare with the threshold. But actually, in the real world, this is not true. So actually, we can say that this amount of value is 1, and then this amount of range is 0, and then this is, we don't know. Okay. Actually, if the signal is in this range, then the system can work incorrectly. Okay. It is because, also, I will explain about some real behavior of electric circuit. So if we just understand some systems digitally, so which means that if we just understand the behavior of electric circuit digitally, then we get the behavior of circuit looks like this, needs to be look like this. Okay, so in this graph, so this is the buffer, as you can see. So it's a buffer, and then this is the input voltage, and then this is the output voltage. Okay, so as you can see, this is the VA, but this node, the input node, the name of the input node is A, and then the name of output node is Y. And then, this is the voltage of Y, and then its x-axis is the voltage of A. So this graph shows the behavior of ideal buffer. Okay, so what is the behavior of ideal buffer? So if the input voltage is range from 0 to VDD, right? Then output is perfectly ground, right? It's a 0 volt, and then 0. And then if the input voltage is in the range from half of VDD to the VDD, then the output is perfectly VDD, and then it's orthogonal at this point. So in this case, noise margin is the half of VDD. This is the perfect system, right? Perfect digital system. But if we want to generate the perfect digital system, or the perfect digital circuit, then the electric circuit needs to work like this. Okay. For the half of VDD, the output is just 0, and then from the half of VDD, then output becomes 1. But this is a perfect behavior, and then there is no perfect devices in the world, right? So actually, this real buffer works like this. Okay. So if the input voltage level increases, then the output voltage is slightly increases, and then at this point, the output voltage level increases dramatically, right? And then at this point, it's saturated, and then the output level looks like this. So in this graph, that we can define the noise margin of this buffer. So we can define the some input range and then output range of this buffer based on this circuit, this graph. Okay, how? So I explained that until this point. So actually, when the slope is 1, okay. So if we just measure the slope of this graph, then if the slope at this point, the until this point, the output is increased slowly. Okay, output voltage level increase slowly, and then we define that at this point the slope is 1. So at this point we just define this is the VOL. So this is the some output. So it's the kind of allowable output from this driver. Okay, because until this point the system works stably. Okay, but from this point, if the input signal changes slightly, but output signal changes dramatically, right? So if we just analyze this graph, so you can find in this range, even though the input values change slightly, very small amount of value is changed, but we can say that output changes very dramatically. So this range is unstable range. So we need to avoid this range in the circuit, right? Do you understand? So input just changes slightly. So this means that the input can be influenced slightly by noise, but the output value changes dramatically. So this system is unstable, right? Do you understand? So we need to avoid this range. Okay, so this is the forbidden zone, and then if you see this buffer, then the slope is 1, then it's saturated. So we can say that this is the output. So this is the VOH. So here, and then if we just check the X value of at this point, then this is the some allowable input. Okay, so because this is the input, so we can say that for this buffer, input range is the voltage input is in this range, then this circuit is stable. This circuit works stably, stably, and then this is some this range. Okay, so because I said that for this range for the input, then this circuit will work in the stable state. Okay, it will work correctly. This range is unstable, so we need to avoid this input range for this circuit, and then this range. This is the some high input range. So we can say that this is stable. Okay. So this range is here. So it's a high input range. And then for the output. So when the output, so we can say that this is the output value, the output value for the stable input. So we can for this input, then output is Upper range is low. Upper range is here, okay? And then for this input, the stable input range, the output range is here. So based on the input and output voltage behavior of this graph, then we can define the output characteristics, the output range of voltage of this circuit, and then the input voltage range of this circuit. Okay, and then we can calculate the noise margin of this circuit. Okay, so it may be tricky because so until so actually in the previous class we learned about the buffer. Then we just define the input is 0 and input is 1. So there are only two cases, right? And then based on this input signal, then output it becomes 0 and 1. Okay, but you need to understand that this is just a translation. Okay, even though our world, our real world, analog world is very complex, and then the signals are continuous, we just translate these signals, the continuous signals to the digital signals, discrete signals. It means that in order to make the simpler system, okay, because our system is so complex, analog system is so complex, then it's not tolerant to the noise, right? That's also very critical problem. But we want to make the some correctly working system. It means that the system needs to be tolerant to the noise. Okay, so we just translate the analog signal to the digital signal, but based on this rule, conversion rule. Okay, and then so actually in the previous class I just explained that the conversion rule is very simple. So we can just compare with the one threshold level, but in reality it's not. So we need to consider the behavior of a circuit like this. Okay, do you understand? So it's a little bit tricky part of the this class, because so in the today's class, as I mentioned, I will just discuss some physical issues, some real issues. The real issues are it's a rather complex, right? So it's a little bit tricky. Okay, so this is the some characteristics, and then how the real voltage signals are translated into the digital signals in a circuit. Okay, and then okay, let's move to the another topic, the voltage scaling. Okay, so I mentioned that so the systems are electric devices, which means that we need to provide the supply voltage. Okay, and then I mentioned that for the modern CPUs, the supply voltage level is around 1 volt, but it was higher for the old generation CPUs. Okay, so in 1970s and then 1980s, the supply voltage level was 5 volt. It was very high, right? But it is reduced, and then currently it is around 1 volt. Okay, then what is the benefit? What is the benefit of this low supply voltage? What is the benefit? Okay. I think that is P equal DI, right? If the I is the same, then the power consumption is determined by supply voltage, right? So this is very simple power consumption, power calculation equation, power equation. So if the I is the same, if the current is the same, then the power is proportional to the voltage, right? So which means that if we reduce the supply voltage level, then we can also reduce the power consumption of a system, right? So we can make the low power system if we use the lower supply voltage. Okay, so VDD has dropped. Okay, then we can save power. Okay, it's very critical, right? So the power consumption is a running cost of a system, right? So the very large data set, like large data center by Google or Microsoft. These large data centers consume huge amount of power. It's similar to the nuclear reactor. Okay, so data center actually consume the electric power. And this amount of electric power is actually similar to the electric power generated by a nuclear power reactor. Okay, so huge amount of power is consumed by large data centers. So power is very critical. The power consumption is very critical to the computer systems actually. But it was 5 volt for the typical digital system. The supply voltage was 5 volt. Okay, but currently it reduced to 1 volt. Okay, so we can save the power, but the performance is also increased. So it means that the CPU includes more transistors. So actually, the CPU consumed higher power actually. But anyway, by reducing the supply voltage, we can save power. Then what will happen if we just connect the higher voltage to the CPU? So what will happen? So sometimes, we can provide higher voltage. For what? If we want to increase the clock frequency of a CPU, and then this is called overclocking, right? And then if we just increase the clock frequency of CPU, then we can increase the performance actually, right? This is called overclocking. So if we supply higher voltage, actually, so modern CPU use the 1 volt, but if we just supply 1.1 volt or 1.2 volt, then we can increase the clock frequency actually. Okay, so which means that if we just increase the supply voltage, then we can also we may increase the performance actually. But if we just supply very high voltage, what will happen? Chip will be broken like this. Okay, so actually we need to provide some appropriate. It's also allowed voltage level, supply voltage level to the system actually. Okay, so actually this is joke. This is just a joke. So if you read the textbook, then you can find this joke in the textbook. Chips, so like the processors, operate because they contain magic smoke. Why? The proof. If the magic smoke is let out, the chip stops working. So like if we provide higher voltage, then the chip will be broken. But when the chip is being broken, then we can observe the smoke from a chip. Okay, so this is a very. So I found that this photo from. So I googled the smoked chip in the Google, and then I found that this photo. Okay, you can find that the circuit is broken. Okay, because we just provide the very high voltage, the circuit will be broken. Okay? Then this is the magic smoke. After the magic smoke is magic smoke comes out from a chip. That chip is broken, so which means that the chip has the magic smoke. Just a joke. Joke in the textbook, not me. Okay, so you can read the textbook here. Okay, and then let's change to the some next topic, transistor. Okay, so you may think that, oh, this is not fun, and then this is a little bit tricky. So why do we need to understand the analog world? Because we are working with the computer systems and the software and then blah blah blah. But why? You can think like this. But this is the kind of some basic knowledge for understanding the physical issues of computer systems. Okay, and then the recently the semiconductor industry is very critical. Then so, but I believe you need to understand why semiconductor industry, why semiconductor technology is critical for the actually computer industry. What? Computer systems. Okay, that's why we are learning about some physical issues of a computer system. Okay, now the next term is the next topic is transistors. Okay, so what is that? Have you ever heard about the transistor? Huh? Okay, okay. Then why? What is a transistor? So if you see the word transistor, then you can find it's a trans. It's a kind of, this word is composed of trans and resistor. Okay. So this is the definition of a transistor from Wikipedia. So you can find that, oh, this is a semiconductor device. Okay, so we can build a transistor using a semiconductors, right? You can also find the semi. Then this transistor is used to amplify, okay, amplify what? Switch. Okay. Switch electric signals and power. So actually we can build CPU chips, digital chips using actually transistors. So transistors are very basic. A transistor is a very basic component for using we can use the transistor to build very complex system. So in the first class, I showed the die photo of the Intel CPU, right? And also I mentioned that number of transistors. A number of transistors in the CPU is kind of around the 5 billion. We can find the 5 billions of transistors in the CPU. So it means that there are many transistors in the CPU chip. So a transistor is a very basic electric component that is used for building digital systems. Right? Oh, we can use the transistor like a switch. Then you can find the 3 terminals here. So I mentioned, so actually you can find the 2 words here, 2 actually verb, amplify and switch. Actually, we use this property for the analog circuit. And then we use this property for the digital circuit. Okay, so I will not explain about this analog property. Okay, so but you can find some amplification here, like here, this range. The input changes small amount of input values are changed, but output values are changed dramatically. This is called the amplification. Okay. Okay. But in a digital system, this range is the unstable range. Okay. So I will just focus on this part, switch. So this property is exploited by digital system. Okay. Then what is a switch? Switch. What is a switch? So we can turn on the light using a switch. Okay, we can turn off the light using a switch, right? Which means, using a switch, we can control the turn on or turn off of devices. Okay, this is the purpose of switch. Then why? How can we use a transistor as a switch? And why is it important? Because we can make a switch using a transistor, but this is the controllable switch. So it looks like this. So in an electric circuit, it's a switch. The symbol of a switch is here. So we can turn on, we can turn off the device using a switch, but this is controllable. Okay, controllable by input signals. Okay, that's why we use a transistor for building digital block or digital systems. Okay, which means using a transistor, we can build basic logic gate. Okay, so using a controllable switch, we can make basic logic gate. That's why a transistor is a very basic component which is used for building digital systems. Okay, so let's learn about the behavior of the switch. Okay, as I mentioned, logic gate. Right? We can build logic gates using transistors. Okay, and then this is the symbol of transistor actually. Okay, and then as I mentioned, so in this definition, it has a three terminals, the three nodes. As I mentioned, transistor has the three nodes. Okay, D, S, G. Okay, so D is the drain, S is the source, G is the gate. A transistor has three nodes, which means that we can connect the three nodes of the transistors, and then we can build electric circuit. And then this is the simple behavior of a transistor. Okay, so this is drain and this is source, and then this is gate. We can use the gate to control the behavior of a transistor. So I mentioned that a transistor is a controllable switch, right? Then using the gate node, we can control the behavior of the switch. And then there are two behaviors, turn on or turn off, right? So this is gate. And then in this example, if the gate value is 0, it's a low voltage, then it's turned off. So which means that drain is disconnected from source. Okay, because this is switch and switch is open, right? So drain is disconnected from the source if the gate is 0. How about this one? If the gate is 1, okay, then drain is connected to source. So this is the turned on state of the switch. So we can understand the behavior of transistor like this. Okay, using a gate, we can control the disconnection and connection between drain and source. Okay, then how can? Okay, so this is kind of some low level knowledge. Okay, so transistors built from actually silicon. Si, so silicon. Okay, actually silicon is a semiconductor. So why is it semiconductor? What is a conductor? Okay, so we can distinguish a material. We can classify material to the conductor. What is a conductor? The conductor includes many free electrons, right? Many free electrons. So which means that if we just connect the voltage sources, then the current flows, okay? Because of many free electrons. Okay, this is the conductor. This is conductor. Okay, and then metals such as the copper, aluminum. These the metals are actually usually conductor, right? And then what is the opposite word of the conductor? Insulator, right? So insulator does not have many free electrons, so the current cannot flow through insulators, right? Conductor is 도체, insulator is 부도체, right? And then semiconductor is 반도체, right? So it is between the conductor and insulator. So which means that based on some situation, but some materials, so actually some so included materials, the semiconductor can be conductor, can work like conductor or insulator. Okay, so that's why it's called semiconductor. So it can work like conductor, so it can work like insulator based on some materials. Okay, so just remember this. So and then based on the amount of free electrons, we can classify conductor and insulator. Just remember this. Then how can we control the property or characteristics of this semiconductor silicon? So actually the silicon does not have enough free electrons. Okay, so that's why it's called semiconductor. You know, the silicon includes 4 electrons, the outer orbit, the last outer orbit. Okay, so that's why the silicon does not have enough free electrons. Okay, and the silicon are connected each other for the 4 directions. Okay, but if we just add some other materials, then we can change the characteristics of silicon. Okay, so for example, N-type semiconductor, N-type silicon. So as you can see, you can find the silicon lattice here, right? This here. So it means that the silicon elements are connected to each other tightly, right? But we can add some other materials, so other elements. So in this example, so we can include the arsenic, okay, piezo arsenic, and then this arsenic includes the more electrons, okay. So because of this arsenic, then this silicon can include the more free electrons. Okay, so this is called the n-type silicon, which means that this is a silicon, but this silicon includes the more free electrons compared to the pure silicon. Okay, this is called the n-type silicon. Then the other type of silicon is called the p-type. P-type. So N means negative, and then p-type silicon. So p-type silicon has the fully positive charges. Actually, there is no fully positive charges, but it means that so we can add the boron to the silicon like this. Then, but this boron has the 3 electrons in the outer orbit. Okay, so which means that the free electrons are the amount of free electrons are reduced, but this reduced free electrons works like the positive charge. Positive charge. And so this is why this is called the hole. Okay, so you can find the free hole here, which means that using this free hole, this free hole works like free positive charges. Okay, so we can make the different type of silicon using other materials like n-type silicon and p-type silicon. Okay, so by combining these different types of silicon, and we can make transistor, and then this type of transistor is called metal oxide silicon transistor. So it's called the MOS transistor. So metal oxide silicon transistor. Okay, and then this is the structure of the MOS transistor. Actually, NMOS transistor. So as you can see, you can find the symbol of transistor here. This is the symbol of NMOS transistor. As I mentioned, actually this NMOS transistor has the 3 nodes: gate, source, and drain. So if you see the structure of this NMOS transistor, so you can find the source is here, and drain is here, and gate is here. So if you see these 3 nodes, then source and drain is connected to the n-type transistor, n-type silicon. Okay, so which means that this n-type silicon has the more free electrons. Okay, and then between the n-type silicon there is p-type silicon, and then this base silicon is called the substrate. So in the NMOS transistor, we use p-type substrate. So which means that there are many free holes. Okay, so which means it's less free electrons in the p-type substrate. Then how about the gate? Gate node is here, right? And then gate is connected to the polysilicon. It's a kind of conductor. And then, but this is a conductor, but we can find the silicon dioxide. Silicon dioxide is the insulator. Okay? So, because there is insulator, the electron cannot pass through the gate to the P-type substrate, okay? Because this is the insulator. Then how can we, so you know, this is kind of tricky. How can we control the switch operation of the transistor? So actually, you know, so just to remember this. So we can control the connection and disconnection of a transistor using gate, right? So we can view the transistor like this. Then how? If gate is 0, okay, so it means that the gate is ground. So actually, this P substrate is connected to the ground, right? And then this is also ground. So if we just check the voltage difference, the voltage difference between gate and substrate P, this is substrate, then the voltage difference is 0 volt, right? So actually, no changes in this transistor because there is no voltage difference. So this is just P and this is just N, this is just N. So even though this N-type transistor has many free electrons, because of this P substrate, then free electrons cannot move between source and drain, right? Do you understand? So it's same to the disconnection of a circuit, right? So I mentioned that, oh, this is P substrate, and then there is less free electrons, and then there are many more free electrons in the N-type silicon. But because of this, this is not connected because of this substrate. So this drain and source is not connected. So this is the off state, right? Understand? But if the gate becomes 1, this is becomes the high voltage, okay? And this is the ground. So we can observe voltage difference between gate and ground. Like VDD is here and the ground is here. Then what will happen? So even though the P substrate has less free electrons, the free electrons can be gathered on the surface of this insulator. So even though the gate is not connected to the substrate because of some voltage difference, then this voltage difference can influence some electromagnetic field of this P substrate. So free electrons gathers the surface of the P substrate. Then what will happen? Oh, we can observe many free electrons on the surface of this transistor. Many free electrons, then it becomes conductor. So which means source and drain is connected. Okay, so you can understand the behavior of transistor like this. So because of free electrons gathered on this surface of the transistor, then source and drain can be connected. Okay, this is the basic behavior of most transistors. Then based on these basic properties or basic characteristics, then we can make the controllable switch. Then using the controllable switch, we can make basic logic gate. Okay. Okay, so I'll stop here, and I hope this can be you can understand this one. Okay. Any questions? Okay. Thank you for your listening, and see you in the next class. 감사합니다.